This is an image of a neuron. A neuron is composed of dendrites, a cell body, axon hillock, axon, and axon terminals. The cell body or soma contains the nucleus. The nucleus contains negatively charged DNA. Outside of the nucleus, potassium is freely floating within the cell. The net charge of the neuron is slightly negative. Surrounding the neuron is extracellular ions, including sodium and chloride. The net charge of the extracellular space is slightly positive. The resting membrane potential of a neuron is negative 70 millivolts. The dendrites of this neuron are receiving incoming signals from another neuron and transmits this signal through the cell via an axon and eventually the axon terminals, where this cell will communicate with another. This video will discuss how this occurs. The axon terminals from a presynaptic neuron receive signals to release a neurotransmitter. The synaptic vesicles will then fuse with the presynaptic membrane and will release the neurotransmitter into the synapse. The neurotransmitter will then bind to the receptor on the target neuron. These receptors are ligand-gated ion channels. Ligand-gated ion channels are a transmembrane ion channel that opens and closes in response to binding to a ligand, in this case a neurotransmitter. The neurotransmitter causes the ion channel to open. The extracellular sodium ions will then move down its electrochemical gradient, rushing into the neuron. If a stimulus is too weak, few ligand-gated channels open, causing a little bit of sodium to enter the cell. This will cause a slight change in the membrane potential in a localized part of the cell and will not cause the cell to reach its threshold. Thus, the cell will return to its resting state. This concept is known as a graded potential. In order to send a long-distance signal through the entire cell, the cell will need a bigger change in the membrane potential to cause an action potential. If enough sodium ions rush into the cell, it will cause the cell to depolarize until it reaches threshold or negative 55 millivolts, and it will trigger an action potential. At this threshold, the voltage-gated ion channels within the axon hillock open and cause a biological chain reaction. These voltage-gated channels will then cause neighboring voltage-gated channels to propagate down the axon. This is known as depolarization, and it will occur until the membrane potential has reached 30 millivolts. Once the action potential reaches the axon terminal, it will trigger the release of a neurotransmitter. The neuron will then repolarize by closing the sodium ion channels and opening the potassium ion channels, causing the potassium ions to rush out of the cell and attempt to reestablish resting membrane potential. However, the potassium channels stay open a little too long, causing the membrane potential to be greater than negative 70 millivolts for a brief period of time. This is known as hyperpolarization. The sodium-potassium pumps will then become activated and will reestablish normal resting conditions where the sodium is extracellular and the potassium is intracellular. To summarize what we have just discussed, I have this graph that depicts the voltage of the membrane potential in millivolts in relation to the time in milliseconds. A neuron who is not at work has a membrane potential of negative 70 millivolts. This neuron will then receive a signal via a neurotransmitter from a presynaptic neuron. The neurotransmitter will bind to a receptor or a ligand-gated channel on a postsynaptic neuron. This will cause extracellular ions, particularly sodium ions, to flow across its gradient and into the neuron. Once the membrane potential reaches negative 55 millivolts or threshold, the cell will depolarize as seen in phase 1 until it reaches an action potential at 30 millivolts. The neuron will then repolarize by closing the sodium ion channels and opening the potassium ion channels, causing the potassium ions to rush out of the cell as seen in phase 2. However, the potassium channels stay open a little too long, causing the membrane potential to be greater than -70 millivolts for a brief period of time. This is known as hyperpolarization and is seen in phase 3. The sodium-potassium pumps will become activated and will reestablish normal resting conditions where the sodium is extracellular and the potassium is intracellular, leaving the neuron with a resting membrane potential of -70 millivolts.